of expunged my brain of how to use Zoom. So I know that we've all become very fluent in Zoom. There might be some point at which I just forget how Zoom works, which is kind of great. I kind of like not remembering how to use it. Okay, got it. Got it. Okay. So I'm going to talk about a few different projects, kind of jumping off from where Brad was starting off. And the first project that I'm going to show is iMonkeyPants, because it's kind of relevant, especially to the trajectory that my work has taken since then. So that this is on the App Store. Share the screen or not. There it is. Oh yeah, I always remember how this little like, no, there we go. Yeah, I love it. So this is an iOS app. And I'm going to demonstrate it because I have it on my iPad right here. It is an app album of algorithmically generated music, where all the sound is synthesized in real time from code in RTC Mix. So in this case, there aren't any audio files even. It's all just code, and it generates the sound in real time. And what that allows me to do is to take motion sensor data, the data from the accelerometer, and map that onto parameters of synthesis so that you can change the music by tilting your device into different positions. So I'm just gonna play one part of one track just to give a sense of what that can do. With the accelerometer, you've got 3 axes, but really only about 2 are usable. You have an x-axis, which reports more or less whether your device is tilted to the left or to the right. If you make quick movements, the values will spike a little bit, but the accelerometer is mostly just going to tell you what position your device is in. So left to right is on the x-axis. The y-axis tells you whether the device is mostly upright or upside down. And there's also a z-axis, which kind of runs through the middle of the device. And if you are manipulating either of the other 2 axes, you are also changing the z-axis, whether you like it or not. And so it's kind of only 2 axes are really usable. This album has 5 tracks, and I'm just going to play a little bit of the 4th one, which is called Self-Destruct, because it was actually, there's a coding accident that turned out just fine. Yeah, an opportunity. Yeah. Has to do with how RTC Mix allows you to declare pitch in this octave point pitch class system. Are you familiar with this?
Yes. Yeah. That's the 8.00.
Yeah. So basically, this track that I'm going to demonstrate, it uses FM synthesis because that's cheap, and because when I started doing this stuff, it was very early days of the iPhone, and it was a very resource constrained environment for real-time audio. So this uses FM synthesis, but basically the carrier frequency, if you cross a threshold on the x-axis, it goes into wildly inappropriate values. So what you'll hear is that on the y-axis, I'm controlling articulation and timbre, and on the x-axis, things change. More staccato, upright. Right. But if we tip it, and you're still controlling articulation here. This is pretty good. Yeah, there we go. So, thank you. This is kind of how I started work in audio programming. In fact, it was in this classroom when I was taking a seminar that Brad was teaching. I think that was like 2013, maybe sometime. Yeah. And I had this idea for this app and no coding experience. And it took like a year and a half to develop the skills I needed to actually make this happen. But I was in grad school and I was supposed to be writing a dissertation, which I did it. That is on my committee, but I was mostly working on this. So the next thing that happened is that a number of years later, Apple informed me that I was going to need to update my app, or they're going to pull it off the App Store because they occasionally clean house. And they weren't bluffing. They
I had several apps and they're gone.
Yeah.
Yeah, because I didn't update it right.
So I did because I still needed a job. No, I did go through the whole process of basically rebuilding the app just so I could resubmit to the App Store. And when you submit to the App Store, everything is reviewed by an actual person at Apple who tests the application. And this app, iMonkeyPants, had been on the App Store for 3 years at that point. So I thought that the review was kind of a formality, but they rejected it on the basis of minimum functionality. My app is not functional enough in any meaningful way, which was dispiriting. And fortunately, they have an appeals process. I went through that process and they accepted it. So iMonkeyPants is back up on the App Store. But it gave me pause about working as a composer using iOS to develop apps, because you could work on something for a long time, but ultimately you don't control whether it ever sees the light of day. And you can't release an iOS app except through the App Store. Like, that is the only avenue. So it occurred to me to wonder if it might be possible to do the same kind of interactive, code-generated, motion-controlled music in a web-based implementation, which it turns out it is. In a web browser, you can also get accelerometer data. And so I composed a piece.
I should point out, this is different. Nicola Hein had shown us some stuff where he was looking at data from the iWatch, okay? And he's basically using that to communicate in the Max MSP. This is done completely in the web browser. Okay? So
Yeah.
It doesn't have Max or anything like that.
Yeah. I composed a piece called "On the Expressive Potential of Suboptimal Speakers," which was my first piece that is a motion-controlled, algorithmically generated composition, but it's entirely web-based. So I'm using the tone.js framework for doing audio programming on the web. Basically, all modern mobile browsers support the Web Audio API, and you could just code directly using the Web Audio API, but tone.js acts as a wrapper around it and gives you a lot of additional functionality. So the code here, and it looks like there's something in the chat. I totally forgot about this chat feature. And also this like interface element is wonderfully located right in the way.
Oh, Ben says he can't.
Oh.
Can you hear me now, Ben?
Yep. Yeah, Brad's mic is muted so we don't get feedback. So when
So
Brad
actually
talks,
talking to
yeah, he's
his
talking to my
speaker.
mic. Yeah. All right. So all the code that powers everything else that I'll be showing today is JavaScript. It's all web-based stuff. So JavaScript is kind of the only way you can deal with it. I prefer working in RTC Mix as just an audio programming language. JavaScript can be a little bit clunky sometimes, but it's great that I can do this on the web. So nice. Yeah. Mm-hmm.
It's like goes everywhere.
That's great. That's good to hear. So it occurred to me that if I could do this in a web-based implementation that doesn't require an app download, that also means that I could compose for a group of people to all play together. I can just give a link and we can all make sound at the same time. So On the Expressive Potential of Suboptimal Speakers is a piece of music for audience participation. And basically you just go to the site and someone says, okay, ready? And you tap play at the same time and it starts making crunchy sounds that depend on how you tilt your phone around. But it becomes a composition for an indeterminate number of people and their devices. after I composed this, it occurred to me that what would be really nice is if I had some way to control when sounds happen on people's devices. With the piece I just showed, there is no communication with a server. And so I have to just rely on everyone tapping the play button at the same time. It doesn't have to be super synchronized, but I have no control over that. But I thought it would be really nice if I could program a server to send cues that would then trigger sounds on any number of clients at exactly the same time. And that's the main approach to composing that I've been taking in a lot of my projects recently, including this piece that is going to be premiered in May that Brad alluded to. So I do want to maybe play some music, and we can all play along. Even on Zoom, you can play along there too. That this is going to work everywhere. But the first thing that we want to do, since I have a captive audience, is I just want to kind of test some stuff. So if you can get out your phone, and if you can go to, actually, I need to share that sound, don't you? Yes. Yeah, but yeah, it'll work on laptop. But
Cool.
What's going on? To share your computer audio, please install the Zoom audio device. That's weird. Well, you might not be hearing computer audio. You might only be hearing, when I do play sound, you might only be hearing it through the speakers here, then played through the microphone. So not the best audio quality, but the audio coming out of your phones will be exactly the same quality that it would be otherwise. I first just want to test things. They should be working. I tracked down a bug and things should be fixed. So if you can go in any browser, Safari or Chrome, if you can go to ryancarter.org/test.
Is that on our phones or
on the phone? Yeah,
okay.
Yeah, mobile device. .org/test, and it'll load some sound files, and then it'll say ready, and yeah, and you can tap start, and then what's going to happen is when you shake your phone, it will meow. No. This one I'm not controlling with the server, so you can tap stop as soon as you're done making meows. Did it work for everyone? Yes? All of you on Zoom? Did it work there? Perfect. Yeah. Yes, very good. So I'm going to, I guess I'll keep sharing because I need to share anyway. So we don't need to do that. So I've been composing music that is for instruments and audience participation on mobile devices. So you go into the concert, you don't even need to know ahead of time that you're going to participate because it's all web-based. And so I get up in front of the audience before the piece starts and I say, get out your phone and go to this URL. And then we do a little bit of practicing. So there are now 2 modes of interactivity for this music. And we've just practiced one of them. The shake mode of interactivity uses gyroscope sensor data. So that responds to when you make quick motions, it will trigger an event. And that is different from what I'm going to be calling the tilt mode of interactivity, which allows you to do the same kind of interactive participation as in iMonkeyPants. So we're going to play a piece together, and this will be a separate URL. This one is going to be, ryancarter.org/hub. This is a piece for Hub New Music, which is in Boston, incidentally. So go to ryancarter.org/hub. And little hub. And I guess I can also put this in the chat if that's helpful. This is a piece called Motion Axis, which there's a whole story behind that. But this is a piece for Hub New Music. Their instrumentation is flute, clarinet, violin, cello. So it's a quartet and audience. And this one I will be controlling from a Q server that I've already logged into. And so right now, you can go ahead and tap start, because you'll see that when you do, the app is currently set in the waiting state. With this, I can, what I do is I code different cues that are either different modes of interactivity or different application states. For example, when a piece is finished, it will shut everything down. When a piece hasn't started yet, it'll just say waiting. And this way I can control all the sounds on the devices, so I can mute everyone if they should not be making sound. Now, the normal thing I do is a little tutorial. So we're gonna do this tutorial. The first mode of interactivity in this tutorial is the tilt mode. So when I increment the Q counter to Q number 1, your device will say tilt, and it's going to be just playing a synthesized tone where the pitch is on the x-axis. So it'll go down and up, left to right, and timbre and volume are on the y-axis. So it'll be softest and most mellow when your device is right side up, brighter and louder when it's upside down. Okay? Get vibrato. And then if your device says tacit, that means you don't play. That is a musical indication meaning silence. So what I can do with these pieces is I can compose a work for instruments and electronics, all diffused from mobile devices of the audience, but I can decide when they make sound and when they don't. And if they do, what kind of interactivity will be involved, whether it's shake, which is the next tutorial, but we already did that with the cats, or whether it's tilt. Are there any questions before we begin? It doesn't all sound like no. I just recently added the cats. We're gonna skip through the shake tutorial, and I need to pull up the score because I'm gonna be the one setting the cue. So if anything is not timed correctly, it's my fault. In the concert, one of the musicians just has an air turn pedal. They just tap the pedal, and that increments the cue counter. So it's the musicians who do this. I don't do this. They just play in there and just next. Yeah. You can, with this panel, you can set cue numbers directly if you're like in rehearsal and you want to skip to cue 12 or whatever. But in a concert, pressing a pedal or pressing the return key will just increment the counter by 1. So this is a piece called Motion Access. The first section, well, I've actually already incremented up to the first section. Q5 is the first section. That's why your phone says tacit. But then you will join at the appropriate time. The piece is like 8 minutes long, flute, violin, clarinet, cello. Any questions? And yeah, if you're on Zoom, it looks like the audio that you'll be hearing will probably not be the highest quality, but the audio from your device will be. Thank you. Thanks.
Really cool.
Thanks. So I figured that now I can kind of just show the code and talk a little bit about how it actually works. But feel free to ask whatever questions you have. I have the whole repo up here. I'm going to try to move this.
The developer mode in Chrome, and I was like, there's a lot of code here.
There's a lot of code. Yeah. Yeah. It's very stable. I mean, so at this point, I've composed, I think, now 6 pieces using this. So 6 interactive pieces. 2 of them are commissions from the Boise Philharmonic that will be premiered in May. One of which is a concerto for orchestra and audience. So it'll be a large orchestra with audience. And the other is a site-specific installation with musicians who will be scattered around a venue, and will also have algorithmically generated sound played back on speakers that's not interactive, but also web-based. And then the audience will be invited to walk around the venue participating, but in that case, the server, that panel, is going to be publicly accessible. So anyone at any point can just tap next and we go on to the next section and they go through a loop. I also built a backdoor so I can take control and I can establish a minimum acceptable duration for a section, because it wouldn't really make sense for a section to be like half a second long. So I can establish like shouldn't be less than 20 seconds or something like that. So this is kind of a project I've been working with for long enough that it's pretty stable. Did anyone have any errors other than Seth? I saw that and I know what's going on there. Yeah. Mm-hmm. No, it's probably more likely data connection. So there are a lot of things going on here. Did anyone on Zoom, did you have any kind of errors? Good. Yeah. There really shouldn't be. Now, if you have, let's say, a whole audience full of people, you have a couple hundred people, and they all have their devices, then if at one point a single client drops out, nobody can really tell except for that person. They don't hear anything from their phone, but 199 phones versus 200 phones sounds the same. However, it would be much less musically effective if the opposite happened. If we're in a tacit section and everyone should be quiet, there, if a single phone makes sound when it shouldn't, that is clearly a mistake and musically marring. And so if the application throws an error at any point, it will shut everything down on that device. It will stop making sound. And that is particularly the case if you lose a data connection, which I think Seth is what happened. If you lose a data connection and it fails to fetch, I'm just using rapid polling. So every 500 milliseconds, it fetches the queue number and the time that the queue is set from the server. If at any point one of those fetches fails, then it'll shut everything down.
Are you using UDP reference? Are you using
No. I mean, it's just, the only protocol is just TCP/IP. Yeah, just goes over the internet. Yeah.
Because UDP will drop packets.
Yeah. I don't want that. No. So yeah, like the technology for communicating with the server is pretty straightforward. Basically, if you are controlling the server, anytime that you set a queue, it just stores that number and it stores the time, because that's really important. The time that it was set on the server is what allows everything to be perfectly synchronized on the clients, and also allows you to drop out and come back in. You probably noticed in the first section where these kind of bell sounds that you're shaking, the pitches are also kind of dissolving and melting. There are all these time-based things I do that rely on the amount of time that has passed in that section. So
it's funny. I noticed it's almost like we're the random number generators.
Mhm.
You're just creating like a general piece of algorithmic composition or something. It has that same effect of kind of scattered masses.
Yeah,
It's
yeah.
really cool.
Yeah,
You know? Yeah.
It's so the devices are all gonna even if you drop out and come back in, you'll be at the correct point in that section. So basically what happens when you first load the page is that it loads the audio files and it loads all the code. And then it does a synchronizing mechanism with the server, where it basically pings the server, asks the server what time do you think it is, and compares it to, because our clocks might not be the same. But I do 6 different round trip pings. I throw away the first one because it could be cached. And if that's the case, then it's garbage. And so there are 5 usable tests where I'm just asking the server what time it is and then logging what time it is on the client. I take the shortest round trip because it's the most likely to be the most precise. And then I estimate the client server delta from that shortest round trip. And so that's how it ends up allowing me to queue things that are going to be perfectly synchronized on every device. Now, I have the score here. I can kind of show you what the notation looks like. I notate all the queues in just numbers and octagon with a label of the kind of interactivity mode. But in most cases, what you have is the moment in musical time when you establish the queue on the server is going to be typically about 1.5 to 2 seconds from the point when that will actually be queued on the devices. It's a very precise system in terms of synchrony, but not low latency. I'm privileging synchrony over latency. So in this case, it's these on beat 3 of this measure, you trigger Q6, and then that's when it actually starts making the sound. That way, it can scale to a very large number of devices because I don't really need low latency. Also, it works fine over cellular. You don't need to be on Wi-Fi. Once the initial page loads, then there's very little data actually going back and forth between the client and the server.
Do you have any problems with firewalls at all? Just because you're using HTTP protocol?
Yeah, no problem with that at all. So basically, the way that a queue looks, this is the first shaking queue. So basically, every queue has a number, and it's I call this whole thing tone motion, I guess is what I've been calling it for myself. I don't actually like advertise it as such because I don't actually give this to people. If you want the code, let me know, whatever. But every time you instantiate a TMQ object, that's what each of these sections actually is. You identify the kind of queue it's going to be. So in this case, a shake. And then the time between when it is triggered on the server to when it should actually happen, when that queue should actually be triggered on the devices. So 1,739 milliseconds is 2 beats at whatever tempo we're at. But then the last argument is the wait time. So let's say that your device does not get the queue by the point when it should be triggered. If it's really essential that everyone start at the same time, then I can set this wait time to 0. And what will happen then is that if you've missed your queue, it will set the app status to a missed queue mode, and it'll just give you an error message that said you missed your queue, but you'll get the next one. However, if it doesn't really matter, like in these shake sections where you're just shaking your device and it's the same sound throughout the entire section, it doesn't matter if you're late to it, then no limit is just a macro that's defined to say, however long it takes for a queue to arrive, even if it's very late, it's fine, it won't be a misqueue. In practice, 1,700 milliseconds is an eternity in terms of latency. So I rarely run up against this issue. So basically, you create an object for the queue. And then there are a handful of methods. The first, there's this go queue method, which is triggered the moment that the queue is, this is called the moment the queue is triggered on your device. So if you want some sound to happen right away, or if you need to start a synthesizer, or if you just need to reset a counter, that kind of stuff. And if it's a shake section, then there's this trigger shake sound method, which is called every time you shake. So in this case, it's just going through an array of pitches, and these are all just different, I recorded glasses. So they kind of sound like bells, but they're actually glasses that are struck. So.
Question, how did you want it for the number 1739?
Oh, I just did the math on what are two beats at chord note equals whatever. And usually I put a comment there. I feel like I normally comment my code a little better. Okay, anyway. So yeah, it's just the amount of time it takes for us to get through 2 beats. So in a shake section, that trigger shake sound is called every time you shake. So you can just do anything in there. And then at the end of a queue, when a new queue is called, it calls this stop queue method. If it's a tilt section, then there is a different method called update tilt sounds, which you can use to update things. This is called by default 20 times per second. So if you need to map something to an axis of the accelerometer, you put that in the update tilt sounds and they'll just update it. In this case, there's a loop here that is handling all of the actual interactivity. This is the Y value. So if your phone is mostly, upside down, it'll be greater than 0.5, that kind of thing.
The 20 times a second, is that just an empirical thing you discovered?
Yeah, it was the same rate of interactivity I use with iMonkey bands, and it's a good rate for audio. Something happens 20 times a second, then that's fast enough to feel really responsive without, the obvious trade-off is higher rates is more computationally expensive. So 20 times per second just kind of works, yeah. So yeah, that's basically how it works. Are there questions? Yes.
For a technical side, it seems that your device is a central clock, and our device has either I'm looking at the switch instead of all the state machines, which are essentially like our device are asking the time, and it's the right time to switch to another mode. Have you considered using, and that's not convenient, but consider using say multiple clocks or more? I would try to imagine if there's only one user here and she's playing this piece and you want to also participate, but perhaps it will only switch to another page, say switch from shape to tone when she did something, like some kind of mechanism there that's not consulting to the central clock.
So you're saying that the user would then control the queue counter, essentially, that the user would be able to control when it goes from one section to another? I mean, I don't do that just because I've developed this for this one specific purpose in mind, which is to compose music for musicians and audience. So I want to retain that control. I want to be able to have everything be synchronized in the control of the musicians, not the audience. But I mean, yeah, like technically, yeah, you could do that. I mean, I could have it you could just put a button there that triggers next cue, that kind of thing. Yeah. Yeah, actually, so every piece has what I call a score file. These are all JavaScript files that are just the code for this particular piece, but then the logic that actually makes it all work is a separate file. So like the fetching stuff is over here. Whoops, what did I just do? Anyway, this stuff. Bug log. Oh yeah, good. Yeah, this is like the code that makes the synchronizing happen, and then the next block does all the queue fetching.
Did you compose the pieces and then after you write piece of music and then go back to code and go back?
I compose everything kind of at the same time, and I compose by hand. So, I just have manuscript paper and I compose out flute part, clarinet part, violin part, cello part, and phone part. I write sonically what the phones are going to do. And then I implement that after I've composed it. And it's sometimes in the process of actually implementing those sounds that I'll stumble on different sounds, or maybe something that I thought was going to sound cool doesn't really work, and I find something that works better. So I end up doing some of the composing directly in the software, but I do plan out to a large extent what the phones are going to do, just paper and pencil, before I actually code anything.
I just have an
Mhm.
idea if you can connect the audience with, like, I mean, for example, there are 100 people in this room listening to this and playing their phones along with this. What if they're like the data each phone has like connected to their website? Is somehow gonna affect each other's sound? Would it be possible to do that?
It would be possible, but much more intensive in terms of network resources.
Oh,
Because then you would have to be sending data from one device to another, which would have to go through the server. And so something like that would be, I think, would be possible. But I've thought about stuff like that, and I'm not sure sort of what kinds of audience member to audience member interactivity would kind of work well. But the one thing I know is that it would definitely, it would be more difficult in terms of how it taxes the network. So more difficult to scale.
There's a way around that in a sense. I got to tell you about a piece. I did a piece with the inaugural concert, the Princeton Laptop Orchestra. I was one of the commission leads. The piece there. Were you at that?
I was the assistant director of the laptop orchestra when
Right.
we did that.
Right. And this piece was an homage to my mentor, Paul Lansky. And yeah, he did a lot of work with an algorithm called LPC that generates like sounds, like voices. And this is back when I was just using MIDI packets on the network. And what I did was there were a lot of times when I wanted the people to be very synchronized with each other. So rather than having them communicate between themselves, I set a master pulse that went out from the server so that every laptop would see that pulse and it would synchronize directly to that pulse. So that's one possible way to sort of get that interaction. Even though it's not actually real, they're not actually synchronizing with each other, they're all just synchronizing with central heartbeat in a way. And it's funny because they did the piece a couple of other times, and we did a show up at Dartmouth. And there, in fact, there's a part where it was all supposed to stop. And I was using the UV packet. One guy didn't stop.
Yep.
But it actually sounded really cool.
Yeah. I mean, that could sound cool, or it could sound terrible.
Yeah. Interesting.
Yeah.
Funny story about that trip. I got bumped up in a terrible hotel with Gobelin.
Oh.
It's a professor at Stanford now. And he got in an argument with his parents in China on the phone, and it lasted for 4 hours.
Oh my God.
And I looked desperately for my field reporter. But
Yeah. I don't know if you guys in the Zoom can hear that, but yeah. Okay. Yeah, you have to stop.
boring
Yeah.
story.
It's anyhow, thanks, Brian. This is fabulous.
Thank you.
I really was wondering what you're up to. This is
Yeah.
amazing stuff. We'll
Thanks.
talk about it more later.
Yeah.
But now we're going to
Yeah.
switch gears.
All right.
I tell you what, why don't you stop your speech here, but let's
Yeah.
keep your
Well,
computer going.
I
okay?
could, or if I log off, then you can unmute.
Yeah.
You know.
That's true.
So I think I'll do that.
Okay.
If that'll work,
Okay,
I'll
so
just,
okay.
unless
That should work.
you wanted to use my computer for the projection. I
Oh,
would.
that's right. Yeah, let's
But-
leave yours on, okay?
Okay. Do you happen to have a charger? Because I will.
Oh,
I-
you need one of those USB chargers. so.
yeah. Mhm.
Good. Cool. Okay, so while Ryan is setting up his charger, I will introduce our next guest of honor. He's joining us virtually from Boston, yay. And it's actually, yeah, right there.
Yeah. Okay.
This is actually his class. I'm just pretending, you know. You've all seen him before, Ben Holtzman. He's been kind of sitting in on a number of these things. And yeah, I specifically asked him to talk about, you know, some of the cool stuff that he knows about that I do not. You know, I mean, squirrel census data is one fun thing. He knows a lot more about like cool stuff. And he's always telling me about how my house on Whidbey Island is going to like fall into Puget Sound any day now. So, and then he shows me the data that says, yeah, see, but of course, to a seismologist like them, any day now is sometime in the next 5 or 10,000 years. You know?
20% chance in the next 50 years.
20%, that's concerningly high.
I'm old. So I'm gonna let Ben take over and tell you what he's got going. And can we shut that air conditioner thing off? I'm not sure I turned it on.
And I can mute and then you can unmute and you can use yours if you want to use your mic to talk now.
That's great.
Whoa.
We will use my microphone.
Okay. You guys can hear me okay, right? You all heard my introduction about Ben. Well, yeah, if you don't know, Ben is a research scientist at Lamont Doherty Earth Observatory here. And he's currently on leave doing fun stuff. And yeah, he's kind of like a major guy. You know, he always gets embarrassed when I say things about him, but you know, he I know he doesn't. Yeah, he was one of the big investigators behind that giant Sumatran earthquake that happened about 10 years ago, was it? Yeah. Well, here's something that's actually true. He for years has been doing this incredible show at the Rose Center called Seismodome. And it's like been this big sellout event. They didn't have it in the last couple of years, but we'll resurrect it someday. Anyhow, and this is his class. So I'm going to turn it over to him and let him tell you stuff that you should be learning that you're not from me. Okay. Cheers.
Yeah. Can you hear me?
Yeah.
Is that good? Okay. Yeah, well, thanks, Brad, for covering for me. And I always, you know, every year as I'm kind of setting up to do the class, I worry that the methods that I've developed for the class and my students are not so accessible to CMC, like the usual kind of people who use Macs and people who are composers. And so it's all in Python. Like that's the only language I know. And so, you know, I think after next year, maybe we'll be able to merge some of these methods and make it more accessible to everybody. But do any of you guys in there use Python regularly?
Yeah, there's a few. Yeah.
Okay, great.
I'm not one of them.
Well, I mean, I always try to teach it at a level where you don't need Python experience, but in practice, it rarely actually works well across a very broad range. So, but I think now that we have all these Max tools, Max RTC, so we use Python to write RTC mix scores. So we're not doing anything in real time, but the ability to do the real time stuff would be obviously great. I mean, you guys are able to do a lot of things that we can't do in my class. Yeah, so like Brad said, I'm a geophysicist at Lamont Doherty Earth Observatory. I've been there for 19 years, I think. And I needed a break. I don't actually get sabbaticals, so this is a fake sabbatical. But what I want to do is show a bit of the kinds of approaches that we've taken in my research group and in my class, and they're pretty some of the projects, I guess there are more seismologists who take my version of the class than Brad's, but so some of their class projects make their way into their theses and stuff.
Somehow I'm not known in the seismological.
But not for lack of my trying. So I thought, yeah, I'll show some of the stuff we've done, a little bit about Seismodome, because that's kind of how the class happened. So one day we start after the Sumatra earthquake, which Brad said, this was 2004. I wasn't actually working. I work on until about the last 5 years, I was only working on the physics of the deep earth, not really on earthquakes directly, but how we use earthquakes to image the inside of the earth, kind of like an MRI, or actually more like a CAT scan of the brain. But then after the Sumatra earthquake, there were a lot of people in my division at Lamont who were working directly on that data. And so I was on tour in Sardinia with a friend, and I played in a big dumb brass band. And he asked me if we could listen to earthquakes, and I thought about it and said nope, but we could take the data and speed it up and turn it into sound. And so when we got back from tour, I started doing that. And the first one we listened to, this was 2005. So it was a few months after the Sumatra earthquake, which was December 26th of 2004. And we asked the head of my lab for if he could spot us by 8 speakers, and we set them up in a ring and took data from 8 seismometers around the planet and listened to the whole Earth's ringing after that earthquake. And I can show you some of that. And then we started, a couple of years later, started coupling that to movies and animations. And it made the questions that people were asking much, much deeper. Like they weren't asking, what do these sounds mean? They were asking, what does that pinging sound mean? Or that rumble, or that, the kinds of, so that the images really helped understand the meaning of the sounds, even though the images, our eyes can't really process moving images that well. Like our ears are much better at picking up temporal patterns. So the idea of starting to use the movies and the sounds together to complement each other, it's a very old idea, but to do it for data and phenomena that are way outside of our range of perception, and to do it for natural data, or natural meaning just things that are in our world, be they sounds that humans create or data that humans create, or completely non-human things, was kind of the idea for the class. But to do it with seismic data at a whole range of length scales was the idea for Seismodome. And I brought this idea to George Lewis in the music department, and he got very excited and told me to go talk to Douglas Repetto in the CMC. And Douglas and I started working together, and he taught me a lot about, well, a lot of things, but basically Python programming for one, for graphics, and then we started trying to write these wrappers to make RTC mix scores. And so that's basically, and then we put together the show in the planetarium. We got a grant to do that. And so I'll just stop talking. So I thought I'd show a few background, so some of the shorter movies from the class, a little bit of the Seismodome stuff, and then a paper that we published a couple of years ago, no, last year.
Yeah,
on-
last year, it's pretty recent.
Yeah. In the Computer Music Journal that did come out of a class project that takes multiple kinds of data and plays them together so that they complement each other to hear really complex patterns. And then maybe if there's time, I'll show you some of the stuff I'm working on now. All right, so I'm going to share some, pop it up. Okay. All right, so this is one of our, everybody see my screen? Yeah, my browser, right?
No,
Mhm.
we're seeing a black screen. It says you started a screen sharing, but we don't actually see anything.
Oh, that's weird.
There we
you
go.
There it is.
Ah, okay. Okay, so we have basically two websites. One is seismicsoundlab.org, and one is a GitHub, Seismic Sound Lab, github.io. This one has a lot more sort of movies, more recent movies, but the Seismodome stuff is really on here. So this is, this is kind of what it looked like in the planetarium. So the audience is down here. No. Yeah, that's not our sound. That like new agey stuff, that's not ours. That, so
we're not
that's,
hearing, Ben, we're not hearing anything.
you're not hearing anything. Oh,
Did
man.
you do a share sound when you shared your?
I did do that, yeah. Oh,
Linux.
Are you on your Linux box?
I am, yeah. Let's just try that again.
Okay.
One more time. If that doesn't work,
Sorry
I'll
about that.
switch. I'll switch to my Mac from 2012. No, that's not gonna work. Oh, man. It's
And
still,
also succeeded in freezing your video too.
yeah,
There you go. Oh, there you go. Okay.
okay, no. But I don't, all right, let's. What? Okay, does that work?
No,
No?
not hearing a thing. It's like it's not talking to the Zoom device or something.
Yeah.
We tried sonifying it with Python.
Ooh, Seth.
I like this Statler and Waldorf. Sitting up in the corner, being grumpy.
Yeah.
He said.
You're gonna put the scientist in residence down in the basement, huh?
It was finally removed from the basement last month. So we're good.
Wow.
All right. Should I just switch to the Mac?
It's
No,
up to
that's-
you. I mean, yeah, I'm not sure what else to do. You can hold your headphones up.
I mean, could we go to that site and play the audio from, I mean, it's just a website, right?
Oh, hey, there's an idea.
Yeah,
Okay,
You know,
we can use your
Yeah.
computer since it's all hooked up.
yeah, if you just put the link in the chat, then I can just go to that URL and you can just tell me what to navigate to and we'll get the audio.
okay,
Yeah, and you'll
All
be able to see it because it's gonna be screen shared. Yeah, great. Good idea.
okay. Oh. And then everyone will have all these links.
True.
okay.
I'm gonna put them in the class webpage too.
Okay. And the sound will be better too. Okay, so
Okay, yeah, it's got it.
if you go, let's see, so I can't, can I see? I guess you should share
Yeah,
your
you can share
screen.
screen, Yeah.
Mhm. You want me to share the screen?
Yeah,
Sure.
Share your sound too.
Yeah. Oh no, sharing sound didn't work with me, did it? No, I can't share sound.
Oh.
We could hear the audio from the site in our class, but it would not go over Zoom.
No.
You go through the mic, yeah. You'd hear the same kind of quality of audio that we.
Then maybe you gotta switch to your other computer.
I'm wondering if it's also, if it's a browser problem.
Oh. You have another browser?
Nope.
I could do it, I suppose. I mean.
Yeah.
Uh,
Mhm.
I'm gonna push this guy out.
Sure.
Maybe I should just drive down there.
Yeah, you'll be able to see it too though, right?
Yeah. All right.
Okay, can you hear me?
With a feedback, yeah.
Okay, hold on, I'm gonna switch and we're gonna show my video too.
This has never happened, and I do this all the time.
Okay, gang.
I don't actually.
Now, come on. All right, there we are. Can you all hear me okay? Hello? They can't hear me.
Yeah, that's fine.
You can hear me okay? Ben, can you hear me? No. Ben, can you hear me okay?
Yes, I can.
Oh, good. That makes me a happy guy. Okay, now let me go here. Seismic Sound Lab. And let me share my screen here. Screen. Stereo. Share sound. Okay, and now I say share. Okay. All right, so now you guys can all see that, right?
Yep. Okay, so go to movies.
Go to movies, okay? Movies. Okay.
Movies, and then scroll down a bit, and that Tohoku earthquake. Yep, up,
So this one,
2011. Yeah,
that guy, okay.
yeah. So this is kind of our masterpiece, I guess, for the seismodome. So what you saw briefly in that clip was as if you're inside this movie, and the screen is the surface of the Earth, the screen of the planetarium, and in the 24-channel sound system, these waves are moving around you, and you're in the center of the Earth.
Okay, shall I give it a go?
Yep. I think, yeah, there you go. So this is 2 hours of Earth time.
So we should be hearing sound now, right?
Not yet.
Oh, good.
There. All right, so the video. Okay. Oh, now I hear myself. That's weird. All right. Brad, I'm gonna log out and call back in
Okay,
from a different computer.
okay, I'll keep a minute.
Okay. And you can play it, go down. You'll see the Oklahoma movie.
Oklahoma. I mean, where the wind comes.
Sweeping. Yeah, that one.
Start singing it.
Yeah. No,
Oh, human.
not that one. There's another. There's a newer one.
Okay, further down.
Oh, no, wait. It's on our Vimeo page.
Human-induced earthquakes and energy. Is this it?
Yeah, actually, go to that climate change one.
Climate change. Okay.
Yeah.
Yeah. All right.
All right. Now go down. Yeah. That. Nope. Nope. Nope.
This one.
That one. Yeah.
Make it full screen.
Yep.
Okay.
So I'll log in. You can just ogle this one for
All
a few
right.
minutes.
Cool. Ben, you're back. Ben, we can't hear you.
That Oklahoma one.
Yeah.
Can you play that guy?
Okay.
The one that's on the right.
Oh.
No, nope. That last. Yeah, there, that guy.
Ooh. Okay. Cool. Ready?
Yeah. Yep.
Here we go.
So these are earthquakes that are all caused by injection of wastewater from fracking. Okay, so these are not, it's not fracking directly, but it's all over the sort of central US where fracking is happening. The water that they use for that process gets too toxic and can't hold any more of the gas that they're trying to extract. And most of the states make that um, illegal to do anything with, except for Oklahoma. Oklahoma said, "Bring it here, and we'll pump it deep in the ground." And so people have been they've been pumping this toxic wastewater from fracking into the ground for quite a while. And then earthquakes started, and it was until a few years ago the most seismically active part of the U.S. What? Okay. Yeah, that guy. There we go. Okay, so there's two data streams here: the injection rate and then the earthquakes.
That's pretty intense. So I guess maybe fracking isn't the best idea.
Yeah. Well, the fracking, when they actually are fracking, they don't make earthquakes because if they did, they wouldn't lose the gas. So they're very careful to not make earthquakes when they frack. But then the wastewater, they want to pump that as far into the rock as they possibly can, so nothing comes back out. And it's at like a mile or two down. So, but what they didn't realize was that they were gonna trigger earthquakes by reactivating old faults that hadn't moved in millions of years. And but for years they denied that there was any relationship between the pumping and and the earthquakes. And then at some point it just became totally undeniable. And an earlier version of this movie, I wouldn't say it helped. It was kind of after that the realization was admitted, but it did kind of go viral in Oklahoma, and um, and and helped. But the thing is, the earthquakes aren't the danger. I mean, there was one earthquake that caused some damage to a town, a few towns. Nobody died, but the real danger is that when you have a fault, that fluid is going to work its way up and into the drinking water, and all the water that people into the aquifers that people use for farming, for feeding animals, for drinking themselves, that's going to be contaminated. But that might be in 10 years, might be in 200 years, might be 1,000 years. So the more abstract, people focus on the earthquakes because they're concrete, but they're not the real hazard. The the and people are less capable of focusing on the more abstract dangers like uncertainty in groundwater contamination or climate change itself, right? So some of the movies we make, the hurricane movie is really, that was a I love that one. That was a student project that it because it turns a data set that, like, there's so much variability in hurricane paths, right? That it's very hard to statistically say these are changing because of climate change, but they are. And the way that one of the things that movie, that last sequence showed, was that the what happened, the hurricane scale goes up to 5, and there was one storm that was so far above that energy level that it broke into 4 storms that were all magnitude 5 hurricane.
Yeah.
And so when you look at the data because the data is all, it's all accessible from NOAA, but it only goes up to 5, right? So when you start looking at the numbers and the proximity of those paths, that made it, and then you explain that storm was orders of magnitude larger than anything that had been observed in the history of categorizing hurricanes. You start to get a picture, but because of the variance is so much bigger than the climate change signal that it's hard for people to grasp what that means.
One of the things that I liked about the Oklahoma movie,
Yeah,
you could clearly hear, I mean, to see the injection rate and then
yeah,
the earthquakes, you kind of like have to shift your eyes back and forth, but you
yeah,
clearly hear the correlation,
yeah, yeah,
because they're two obviously different sounds.
yep,
That was kind of a really neat sort of demo of the joys of sonification, I think.
yeah, yeah. And that was something that we learned how to, how do you, if you have a signal that's very irregular, like the earthquakes have a lot of randomness to them, right? Then the other data is very evenly spaced and is tonal. So the earthquakes are a broadband signal with energy across a very wide range of frequencies. And so having a clear tonal signal that's evenly spaced in time was sort of a way of separating those two pieces of information. And what I want to show, okay, so
Do you want to try sharing your screen now? Do you want me to stop?
yeah, yeah. Oh, yep. Okay. So, so what in the one of the things I thought might be useful as you guys are thinking about your projects. These are the notes from my class, but we kind of separate these methods into ones that we call direct sonification. So all the seismic data are oscillatory signals, right? They look just like sound waves. So those are the ones that we can just speed up, right? And there are other things that can, like you can do that with tides or with length of the day or temperature, like daily temperature signals are something, those are oscillating around a mean, and the mean might be drifting, but you can filter that out, or you can sonify that as well. But you need to make a sound, a direct sonification, you need an oscillatory signal. And then on the far other end are just pure representation of some data with tones, right? And that's what I think Nicola had the example he showed last week. There was an example of something that was just, the data was being mapped from the phone motion, was being mapped purely to tones. I would say what Ryan you're doing is something in the middle, right? Where you're it's not the the pitches themselves aren't governed by the data directly, but how they fade in, how they fade out, the the sound properties, or maybe the sequence, but not the tones themselves.
Yeah, and in some cases the pitches are determined, especially in the tilt sections. A lot of times it's synthesized, and I'm actually controlling pitch.
Okay, yeah. So, but that's also a more of a modulation in some cases, and then granular synthesis is so these are all RTC mix. Everything but direct sonification, we're using RTC mix instruments, and granular synthesis is one that we use a lot because it has a lot of the randomness that is inherent to the patterns that we are trying to represent. So the hurricane tracks was using granular synthesis, and the mean, the kind of pitch center and the width of the granular synthesis was the. Have you guys talked about grand synth yet?
Not explicitly, but a lot of the stuff we've done has been that. It's basically
Okay.
just little grains of data, the little beats
Yeah.
and stuff. That's basically what it is.
Yeah.
I mean, pretty much all of the sonification we've done has been like little blips of data, like how many squirrels are there. And well, that one was
Right. That's squirrel synthesis. Each squirrel is a grain of
It's
sound.
been a pretty squirrely class since you haven't been here.
Yeah. I don't know what squirrely means.
That's because you're from Boston.
I'm from California.
Well, same thing.
So this is kind of the limit. With direct sonification, you can change the pitch, but you can't do that independently of the duration of that signal, because all you're doing is changing the time step that the computer thinks exists between each data point, right? Then there are some ways of getting sort of time stretching without pitch shifting, or pitch shifting without time stretching, but these are very limited in terms of the departure from the actual time scale of the data. So we quickly moved to tonal methods. And what I just want to show quickly, because these are things you might want to use. There, and you can rewrite them in Max. But this is taking some arbitrary data in red and sampling it evenly in time. And there are times when you want to do this, but it doesn't convey as much of the dynamics as if you take that data and instead of sampling in time, you decide what pitches you want, right? So you decide the pitches that the range of data is going to be mapped to, and then where those frequencies occur in the data determine when they occur in time. And what that does is when something is changing really quickly, you're going to hear a and then it's going to slow down. Like this beat is much slower, and then there's a very dense rhythm, and then it slows down, dense, slows down, and this conveys a lot of dynamics that that other ones don't. And then there's the mixture, right? Then there's like, if you want to determine the pitches and then find the kind of nearest time to when it would occur in the data, you can push it one way or the other. And so I'd be happy to.
That's funny because this shows my ignorance. I mean, virtually everything that I've done in this class has been the first type, where you basically just do sampling of the data and you just kind of step through it in time. This is actually really intriguing. I hadn't seen this before. Huh. Yeah.
Well, I'll send you, the codes are all um, on GitHub, and um, but and then we had another thing we've done is like building up chords. So if this is the same data, but where a tone, a value occurs, it's going to start an oscillator, right? And that's going to keep going until that data reoccurs. So this is a chord being built up. So this makes a really big kind of a swelling sound. And there's some gaps in here. I don't know what happened, but um, this should be a line going across. This guy should be going across all the way, but I think we fixed that. Anyway, these just make swelling chords, and that's a very underlying kind of like you feel that you may not hear it so clearly, but
We did do that with the squirrels.
swelling squirrels. That's
They were building up those squirrels.
yeah.
Yeah, basically the number of squirrels per hectare was determining how many notes of the word.
Great.
Yeah.
Um, okay, so I'll just show. We don't have a whole lot of time, I guess. But I want to show you this movie we did on a geyser. So these are geyser dynamics, and I just gotta find the paper. One sec. Okay. All right. So this was in Computer Music Journal, which I used to read when I was procrastinating my chemistry homework in college. And so to have a paper in here was really felt great. But so Anna, Arthur was a postdoc in my group, and Leif is a volcanologist, and Anna is also a volcanologist. And people use geysers as kind of small analog experiments, like natural analog experiments for volcanoes. So this was a geyser. It's called Lone Star Geyser in Yellowstone, and it's not like the famous one, so people can put instruments all over it and not worry about tourists. But essentially, there's an underground plumbing system, and then there's jets, and then the ground is going up and down as the fluid down here changes pressure. So as there's an injection of fluid, and what happens is you get these kind of cavities that fill up with fluid and then are coupled to what essentially become like valves, kind of like a bagpipe or like, and so uh, these are all kind of coupled processes. Like what happens in these valves determines how easily this fluid can get out and how much pressure is going to build up in there and before the next eruption. So volcanoes erupt, every 10 years or 100 years, and geysers erupt every 10 minutes or an hour or 2 hours or 3 hours. So it's kind of the same physics at a smaller scale. And so what we did was take different kinds of data. We took let's just watch the movie. The paper's all black and white. Okay, over here. there's a rule in my class that you have to make an explainer, some slide or some version of the movie that's simple and explains what the sound and movie are representing.
Ben, should we be hearing sound now?
Oh man, no.
Okay.
But I don't know if I shared. I don't think I shared sound.
Okay.
Yeah. Okay. Wait, what did I just do?
I don't know.
Here we go. What? Oh, huh?
We're seeing that black screen again. Oh, there you go.
Okay. Okay. Here we go. All right. So we have the ground tilt. So there's a tilt meter that's just basically an accelerometer measuring how the ground is tilting. And then we have seismic data from one seismometer. And we did something pretty sneaky with that one seismometer data. So you'll hear it moving from left to right. And I can explain after if there's time. And then we took an infrared camera pointed at the spout of the geyser, and that the temperature is a proxy for how fast the fluid in the jet is moving. Because if it's moving slowly, it cools off more, so the fluid's cooler. If it's moving fast, it's closer to the temperature that it was in the ground. So this is 10 hours of data. So right, you look at the data, it's kind of boring, and I mean it's neat, but you don't really know what it means. Okay, so that's the discharge. This is the seismic tremor. And then this is the tilt.
So cute.
Extended. Yeah. So the thing about like the they're very regular in the timing of the eruptions, but each eruption is totally different. Okay. So, are there any questions on how we made those or anything?
What
Um,
what did you use for the graphics of the geyser? That's really impressive.
oh, we used a digital elevation model for the surface, and then I just drew something for the plumbing
Ah,
underneath,
wow.
and then we used Python. It's pretty simple Python graphics,
Huh.
just for the moving bits.
Cool. Yeah.
And so in the paper we explain the methods. I came up with an algorithm that for the this thing for the tilt that basically is moving through a chord. And so if you listen closely to it, you hear beats. That's because they're neighboring tones that are overlapping in time, that are very close, and that's like what's happening is just it's sweeping each of these triangle filters is determining an envelope in time for each pitch. So as the data moves through a given triangle, it's writing out an envelope filter, an envelope, and then you multiply that envelope by an oscillator, and you get these kind of sweeping through a chord. So it's not the swell that I showed earlier,
Yeah.
and then the others, I think grand synth for the temperature, and then a direct sonification for the seismic. So
Hmm.
kind of mixing those things has been what we've been trying to do in the last few years, sort of figure out how to use multiple data streams in parallel to help you
Yeah.
pick up
That's
their interactions.
that's one of the things I haven't done in the class really at all. My wife actually had this great idea about choosing a consonant chord to represent a normative state, say between two temperature sensors, and that if you could hear the consonants kind of
Yeah,
disrupt, it might be kind of a fun thing to do too.
yeah.
Yeah.
Yeah,
Anyhow, well,
I
hey, we're
guess we
about
should stop. Yeah.
yeah. This is great though,
Um,
Ben. Thank you so much. And
sure. Yeah.
yeah,
Sorry for the technical difficulties.
that's okay. Yeah. It's not as if I haven't had a few. Like when I typed in the IP address wrong. How come it's not working? Dummy. Okay, well, thanks, Ben, and thanks,
Yeah.
And before we go, I'm going to shut off the recording, but don't leave quite